Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language lecture series, where today we're going to be discussing non-zero whole number exponents. And to introduce that topic, here's a question that you can think of asking somebody and see what they answer off the top of their heads. If I say to you, how much is 3 2s? What answer are you most likely to give me for that? To give you a hint, I expect it to be 6, okay? But here's what happens. When I say how much is 3 2s, can you visualize a first grader just saying, oh, it's 222. Or, as the usual guess goes, 2 plus 2 plus 2. But it could also be 2 times 2 times 2. In other words, just as there are occasions where we may want to add a number to itself several times, there are other occasions where we want to multiply a number by itself 3 times. So, in other words, if you were trying to be precise, what the question should be is either how much is the sum of 3 2s or how much is the product of 3 2s. And I'm going to give you an illustration of when you would be multiplying 2 by 2 by 2. See, let's suppose you have 3 fair coins, a penny, a nickel, and a dime, and they're flipped. In how many different ways can the coins turn up heads or tails? And you may have noticed that I put the word fair in quotation marks here. See, a fair coin means that it's equally likely that the coin will turn up heads or tails. For example, suppose each of the 3 coins had a head on both sides. Then there's only one way they can turn up. They can turn up all heads. That's the only possibility they have. So a fair coin means the coin is unbiased. And I thought this is a good place to introduce a connection between what we call probability and what we call statistics. See, to know whether a coin is fair or not, you would have to keep flipping it and keep track of how it turned up. And after a while, you make the value judgment that it's a fair coin. That process is called statistics. Once you've said it's a fair coin, then you can proceed accordingly. And the way you protect yourself in math is don't do what I did over here. Start every math problem of this type with the word if. If 3 fair coins, a penny, a nickel, and a dime, are flipped, comma, in how many different ways can the coins turn up heads or tails? That way, it eliminates any possible debate that people might want to make about how do you know the coin is fair? Well, I said if. If doesn't mean it happened. It's under the condition that this happened. Every math problem basically has an if attached to it, okay? Just thought I would mention that. But let's see what happens now. In case we lost track of the forest because of the trees, the problem was the 3 fair coins, a penny, nickel, and a dime, are flipped. In how many different ways can the 3 coins turn up heads or tails? Well, notice the penny can only come up in 2 ways. It's either a head or a tail. By the way, these outcomes numbered 1 and 2, that's not a preference. It's just, it could have been outcome number 1 was tail, outcome number 2 was tail. Is that there are 2 possible outcomes, okay? Now, here's the point. Now you're going to flip the nickel. The nickel doesn't know whether the penny came up heads or tails. So what could happen is, whether the penny came up heads or tails, the nickel could have come up heads. Or even if the penny turned up heads and tails, the nickel could have come up tails. So we've doubled the number of possible outcomes. In other words, both coins could have turned up heads. The nickel could have been heads and the penny tails. The nickel could have been tails and the penny heads. And the nickel and the penny could both have been tails, okay? Now let's see what happens when we throw in the dime. The dime doesn't know what's happened here. All the dime knows is it's going to be flipped. Well, if any one of these 4 combinations turned up, doesn't matter, the dime could have turned up heads. And these same 4 combinations could have occurred even if the dime turns up tails. You see what's happening? Each time we add on a coin, we double the number of possible outcomes. For example, we abbreviate 2 times 2 times 2, and we read this as 2 to the 3rd power, okay? If b is any number and n is any positive integer, b to the n, notice I said b to the nth power, denotes the product of n factors of b. For example, b to the 5th power means b times b times b times b. Be careful, don't say it's b multiplied by itself 5 times. B is only multiplied by itself 4 times. It's that altogether there are 5 factors of b. Or another way of looking at it would be, write this, 1 doesn't change anything. Say it's the product of a 1 followed by 5 b's, okay? B to the 7th power would be a 1 multiplied by the product of 7 b's, etc. B is called the base. Maybe that's why I picked B for base. And n is called the exponent. And b, as I say this, I'm reading it. This is read as b raised to the nth power, or b to the nth, just for short. Okay? And let me show you what tends to happen here. Students will often confuse the sum of nb's with the product of nb's. In other words, we know that 3 times 4 is 4 times 3. Students very often, because they're not used to the notation, will look at 3 to the 4th power and call it 12. No, 3 times 4 is 12. 3 to the 4th power is 3 times 3 times 3 times 3. And notice that even though 3 times 4 is equal to 4 times 3, 3 to the 4th power is not equal to 4 to the 3rd power. See, 3 to the 4th power means what? 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, times 3 is 81, so that's equal to 81. On the other hand, 4 to the 3rd power is the product of 3 fours. 4 times 4 is 16, times 4 is 64. So we see that 3 to the 4th is 81, but 4 to the 3rd is 64, so they're not equal. And by the way, do you notice that this gets more and more tedious as you keep going to a higher power? See, 4 to the 4th power would be what? I got to multiply this by 4. To the 5th power, whatever I get, I got to multiply that by 4. So if I wanted 4 to the 20th power, I would have to take 20 factors of 4. Now you might say, who in the world would ever want to take 20 factors of 4? Well, suppose there's a multiple choice exam, and there are 20 questions, and for each question, the multiple choice that you have are four choices. In other words, it can be A, B, C, D for the first one, it can be A, B, C, D for the second one, etc. So in other words, every time you add a question, you're multiplying the number of possible outcomes by 4. And since there are 20 questions, there are going to be 4 to the 20 possible ways in which the true-falses can be arranged. Fortunately, we have something called a calculator that will compute things like this for you. On the calculator, and not all calculators are the same, but for the most part, you will see an X to the Y key or something that looks like that. What you do is you input the 4, press the X to the Y key, input the number 20, hit the equal button, and the answer will appear. What number is this? See, units, thousands, millions, 1,999,511,627,776 possible outcomes. So if you came into the test completely unprepared and just did guessing, your chances of getting all 20 of these right is 1 chance out of over 1 trillion. And these are the kind of things that govern odds and things like this when people make bets and the like. What is the possibility? How many outcomes are there? How many are favorable? And here's an interesting one. Do you realize that, and this mystifies people sometimes, if you double 2 20 times, or I should put it this way, if you take 20 factors of 2, the answer is already bigger than 1 million. In fact, to be exact, either using the calculator or longhand. And what do I mean by longhand? Well, if you have 20 factors of 2, if you know that 2 to the 5th power, 2, 4, 8, 16, 32, is 32, every 5 factors of 2 can be replaced by 32. So this would be 32 times 32 times 32, then 32 times 32 times 32. You could do that very quickly on the calculator, or at least a lot more quickly than punching in 20 factors of 2 over here. And you get that the answer is 1,048,576. And this leads to something which I think is kind of exciting, has nothing to do with math, but has a lot to do with being kind to people. I call it the power of 2. If you went out and helped just 2 people, And in response to that, each of those two people went out and helped two other people. By the 20th link in the chain, you will have helped over 1 million people with no one having to have helped more than two people. Try imagining trying to help 1 million people all at once. But think of how simple it could be just to help two people and have each of those two people go out and help two people. Of course, science is neutral. There's a downside to this also. Since 20 factors of 2 multiply out to over 1 million, if one person is infected with a disease, if that person goes out and infects two others, and each of those two people go out and infect two others, then by the 20th link in the chain, over 1 million people have been affected with the disease. So in other words, 2 to the 20th is over 1 million, whether you use it for good or for evil. The math is amoral. It doesn't make a judgment. How we use it is the big thing. But anyway, enough lecturing on morality. Most people say, well, show me the money. One of the nicest places that exponential growth works is in terms of making investments where the interest is compounded annually as opposed to, say, simple interest. Now, what does compounded annually mean? Well, suppose I put $10,000 in the bank, and after the maturation date comes, let's say it's 10%, okay? So now it's worth 11,000, okay? I made $1,000 plus my 10,000. The following year, it's the 11,000, not the 10,000, that's gathering the interest for me. So let's suppose, for the sake of argument, that your investment doubled every 10 years. In other words, if you put in $1, in 10 years it became $2, 10 years later it was $4, 10 years later it was $8. It keeps doubling every 10 years. Well, instead of $1, suppose the adjective is 10,000. Suppose we put in $10,000. After 10 years, the investment is worth 20,000. After 20 years, the next 10 years, it's worth 40,000. See, it's doubling every 10 years. After 30 years, it's worth 80,000. After 40 years, 160,000. After 50 years, 320,000. In other words, in 50 years, okay, this is why long-term planning investment is important. You put away $10,000 now, if it will double in value every 10 years, 50 years from now, the value of that investment will be $310,000. Sort of an amazing result. And by the way, that works negatively also. If you notice on your credit cards, they give you your balance at the end of the month. They also give you the minimum payment. If you have a big enough balance and you keep paying the minimum amount, you'll be running into a problem like this in the negative sense. The amount of money you will pay to pay off a modest amount of money will be monumental compared to the amount that you borrowed. But anyway, this is sort of an idea of what goes on this way. We don't have to keep thinking of doubling. Here's an interesting one. How many different numbers can be rolled by a pair of dice? Well, the smallest, remember, a die is what? A 6-sided figure. That's why they call it a cube. The cubes, okay? And it has anywhere from 1 dot to 6 dots, okay? So the lowest amount you can roll is a double 1, which would be 2. The biggest you can roll is a 12, which is a double 6, and all the numbers in between. In other words, there are only 11 different numbers that can come up when you roll a pair of dice. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. However, there are 36 different combinations, because each die has 6 faces. So we can distinguish between them. Let's suppose one is colored red and the other is colored green. Okay? We roll the green one. It can come up in any one of 6 ways. It can be a 1, 2, 3, 4, 5, or 6. Now we roll the second die, the red die. It could come up a 1. It could come up a 2. It could come up a 3. It could come up a 4. It could come up a 5. In other words, they're going to be what? 1, 2, 3, 4, 5, 6 possible, 6 events, each with 6 possible outcomes. See, and here's where people get tricked in terms of probability. Why gambling houses don't have to be dishonest. People will make them a lot of money even by the gambling house being honest. A typical gambling house event might say, if you roll a 12, we'll pay you off at 25 to 1. For every dollar you bet, we'll give you back 25 if you roll a 12. Well, you say, my goodness, there's only 11 different numbers that can come up. So I get one chance out of 11. No, you have one chance out of 36. There are 11 different numbers that can be named, but 36 different combinations of the dice. And the only way you can roll a 12 is to get 2 sixes. That's one event out of a possible 36 outcomes. The odds against you are 35 to 1, not 25 to 1, okay? And certainly not 11 to 1. See, this is now the reason that 7 is such a popular number with dice is that the 7 can come up in more ways than any other single combination. See, you can get a 4 and a 3, a 6 and a 1, a 5 and a 2, and then the reverses depending on which is the red die and which is the green die. At any rate, I think you get the knack of why exponential notation can be very important in certain types of mathematics problems, pure math problems, probability, investment, a whole bunch of things like that. So let's close for today just with a relatively simple problem. And basically the practice problem today will be if 4 fair dice are rolled simultaneously, how many possible outcomes are there? And remember what you do now, you pause the video, work on the problem, and then come back and resume watching the video when you finish so I can show you my solution and make a small comment on it, okay? See, so what happens is, when you roll the dice 4 times, the first die can turn up in 6 possible ways. No matter which of the 6 possible ways the first die turned up, the second one can also turn up in 6 ways. That gives you 6 times 6, or 36 combinations, okay? Now, no matter how the first 2 came up, there's 36 different ways they could have come up. The third die can come up in any one of 6 ways, so it's going to be 36 times 6, which is 216. And as you go along here, you see that in each row, the number under the number of possible outcomes is 6 times the number it was in the previous row. You can look through this chart and notice that, so by the way, the answer to our problem was we wanted to see how many possible ways there were when 4 dice were rolled simultaneously. The answer there was 1,296 possible outcomes, which means that if you were betting on 4 sixes coming up, for example, you'd have one chance in 1,296 of being correct. And this gets, look how fast these numbers grow. If there were 8 dice that were rolled simultaneously, the probability of getting all of them to turn up one particular outcome, one particular way. In other words, let's say you wanted all 6s to come up. Your chances would be 1 out of 1,679,616. And again, what I want you to notice is, and this is sort of an important wrap-up type of thing, with the advent of today's technology, computations can be done fantastically fast, okay? Things that you commit to memory can be recalled, if you forget them, almost instantaneously by going to Google or to Wikipedia or a whole bunch of number of things that you can do. What you can't duplicate on the internet is the logic that goes behind why you want to make the computation. And this is why it's so important for us to emphasize what the rules are and the like. And even for students who aren't going to go on in the math science field, for them especially, the most important thing that they can take away from a math course is the degree of logic that you have to use, because later on in life, you can get through life without knowing how to solve a John and Bill marble problem, but you can't get through life successfully without knowing how to make logical conclusions. At any rate, this was just my mood day for sermonizing a little bit, but I just felt like doing this, and I hope you see an amount of growth coming out of this that can help you and your students. In any event, we will have our final lecture next time when we'll talk about exponents from an algebraic point of view primarily. But until next time, stay young, have fun. See you soon.